Assalamualaikum and hi everyone. Now we are going to discuss the still the heat equation, okay, but with a second type of boundary condition. Okay, so now we have the insulated endpoints. Okay, so you can imagine you have a rod. Um, you have a rod, and at the left and right endpoints, you put the some material. Okay, so you put some material at the left and also at the right. This material is a non-conductive type, okay, non-conductive material, or simply you can say material that is resistant to the heat. Okay, therefore, no heat flow should be coming in or going out from your rod. Okay, so that is what it means by insulated endpoints. Mathematically, it is shown by the derivative here. Okay, u subscript x simply means del u del x. Okay, so at the left you have at x equal to 0 and t. Okay, is 0. Okay, so this is equal to this. Okay, so mathematically, the insulated endpoints is given by the del u del x. Okay, meaning that the rate of change of the temperature with respect to your location, with respect to your spatial coordinate. Okay, so at that point, meaning at the left and also at the right, you can see the derivative of both equal to 0, meaning that no heat, okay, can go out or coming in. Okay, so that's what it means mathematically by the insulated, okay, insulated case, right? So both value at the left and at the right are equal to 0, and we also have the initial condition at time t equal to 0, the temperature u is given by x, so it depends on where you are. All right, so your first step, just like before, your first step is to convert the PDE to the O. First of all, we are going to assume our solution to be in the form of uxt equals x, which is a function of small x times t, okay, which is the time, okay, t of t. Okay, so I'm going to put this one as the star here. So this is our assumption, right? And then in the heat equation that is given to us, okay, at the top here, we have del u del t. Okay, so meaning that we need to differentiate u with respect to the time. Okay, so it means x follows. So I'm going to discard the small x. Okay, but you should know capital X is actually a function of small x. Okay, and since we just differentiate respect to t, so here we have t prime. All right, and in the equation we also have del square u del x square, meaning that we differentiate u twice with respect to x. So we have x double prime and t follows because del square u del x square simply means the t should be regarded as constant. So the t follows, right? And then we substitute, okay, substitute into the PDE. Into the PDE. Okay, PDE means the heat equation that we have. Okay, so therefore we have del u del t, which is x t prime equals, so we have here del u del t equals to alpha square. Okay, so we have alpha square and del square u del x square is x double prime t. Okay, separating the variables. Okay, so we put x double prime to be on the top. Okay, so over x, okay, equals, so this is just manipulation, a bit of manipulation. So we have t prime over alpha square t. Okay, so the same justification as before. Okay, so these two terms at the left and at the right, they will be equivalent to each other if they are both constants. Okay, constant. Otherwise, they should not be equal to each other because at the left we have function in terms of x only. At the right we have function in terms of small t only. Okay, so they will never be equivalent to each other unless they are constant. Okay, so left hand side equal to right hand side, okay, when they are both constant. So we denote the constant as lambda. Okay, so x double prime over x equals lambda. Okay, then we have x double prime over x equals lambda. Then we rearrange, we have x double prime minus lambda x equal to 0. Okay, so this one denoted as equation 1. And then we have t prime over alpha square t also equals lambda. So based on that, we have t prime minus lambda alpha square t equal to 0. So this is equation 2. Now equation 1 and 2, okay, are the ODEs. Okay, they are ODEs because you have a function. Okay, so the first one is a function with respect to x only. Okay, in the form of x only. And the second equation is a function in terms of t only. Okay, in fact, okay, for every x and t here, okay, it should be denoted as a function of small t, and at the top here is a function of small x. Okay, so they are ODE because it is differential equation, okay, that consists of a single independent variable. Okay, so that is the definition of the ODE. Okay, so that is your first step, is to convert the PDE to the ODE. Step number 2 is to form the boundary conditions for the ODE. Okay, so we need to find the boundary conditions for the ODE here, because when we solve equation 1 and equation 2, we are going to produce constant. Okay, so in order to get the constant, we need to have the boundary condition. We need to use the boundary condition in order to know the constant that we will produce later. Okay, so we need to find the boundary conditions for our ODE. So we are going to use the given condition, okay, the given boundary condition. So we are going to use these two in order to create another two boundary conditions for the ODE. All right. So the first boundary condition that is given to us is u x 0t equal to 0. Okay, but somehow we cannot use this one directly, okay, because we don't have the equation of ux yet. All right, so it simply means we need to differentiate equation star. Okay, we have this equation here, equation star here. So we cannot use this condition directly to this because this is uxt. This is not u subscript x. This is not the derivative yet. Okay, so that's why we need to differentiate that equation first, okay, before we can use the given condition. Okay, so from the equation star, okay, so ux xt, okay, simply means you differentiate u with respect to x, so you are going to have this, okay, because you differentiate x. All right, so now you can use the condition, okay, because you already have the equation for ux. Okay, so when x equal to 0, the u subscript x is 0. So at the left you have 0, at the right you have x prime. Okay, small x is 0, and this is still the t. Okay, and then we know that, okay, the t cannot be 0. Okay, so t of t cannot be 0 because if it is 0, okay, if t is 0, the whole thing here will be 0. If t is 0, then you are going to have u equal to 0. Okay, so it simply means, okay, if you have the rod here, if u x t equal to 0, then you have, okay, for any location x at any time t, the temperature is always 0, which is not true. This is not valid to our application. Okay, so that's why we say that t of t cannot be 0. Then in that case, okay, so x prime of 0 need to be 0 in order to have this equation here equal to 0 at the left. All right, so x prime of 0 equal to 0. Okay, so it is 0 only at the point small x equal to 0 here. So that it's okay to have x prime, okay, equal to 0. And then so this is our condition that we now have. We produce on our own. And then we have the second condition, u x l t, which is also equal to 0, okay, at the right point. Okay, so based on the equation that we have differentiate here, so it means at the left hand side again we have 0, and at the right hand side we have x prime of L. Okay, because at this condition the value of x is L. Okay, so we have x prime of L and then t of t. Okay, so the same justification, t of t cannot be 0, then therefore the one that need to be 0 is x prime of L. Okay, equal to 0. So now we have this one and this one, which is our boundary conditions for the ODE. Okay, so when we solve the ODE, we are going to use these two boundary conditions. Okay, so that is your second step. Okay, step 3, we need to consider all cases of lambda. Okay, because up here we have equation 1 and 2, so we have lambda in the equation. Again, lambda is constant. Okay, so constant could be 0, it could be a positive number, or it could be negative number. So we need to consider each, okay, of the cases. All right, so case number 1 is when lambda equal to 0. Okay, lambda equal to 0. Okay, so now we can see the effect when lambda equal to 0. Okay, from equation 1 here, when lambda equal to 0, we have x double prime equal to 0. And for the equation 2, when lambda equal to 0, we have t prime equal to 0. Okay, so we can say that from equation 1, okay, when lambda equal to 0, we only have x double prime equal to 0. So this is the homogeneous, okay, homogeneous equation. This is what you have in chapter 2 before. Just that in chapter 2, you are dealing with a y, okay, y double prime, okay, y prime and so on. Okay, so in this chapter, you have x double prime. Okay, but the solutions are basically follows the same procedure. Okay, first you need to get the characteristic equation, m squared equal to 0. So it means you have two roots, m1 equal to 0, m2 is also equal to 0. Okay, so you have equal roots. Okay, so therefore your solution here should be x equals a plus bx. Okay, so basically you have this one in brackets, okay, a plus bx in bracket, and then you need to multiply with the exponent m1 or m2x. Okay, since your m equal to 0, so you have exponent which is 1, exponent of 0 which is 1. So you just you can ignore the exponent term. Okay, so we have a plus bx. So this is our initial solution. Okay, so now we are going to get the a and b. Find a and b. okay, by using the boundary conditions that we have obtained in in step 2. Okay, so highlight here, this is your solution, general solution for the X, general solution for ODE 1 here. Okay. Okay, now your first boundary condition that you obtain in step 2 is x prime of um, x prime of 0 equal to 0. Okay, so that is your first one here. Okay, but before you can use this one, you need to have the equation for x prime. Okay, here you only have equation for the x. This is not the derivative. Okay, so it means you need to differentiate x prime first. Okay, so somewhere here, x prime of x is b only. That is the derivative. Okay, so now, when you have x prime 0 equal to 0, so based on the equation, the derivative, then at the left-hand side you have 0, at the right-hand side is b. Okay? So 0 equals b or b equal to 0. Then you update your solution. So update. Your current solution would be x of x equals a, because your b is 0. Okay, now let's try to get the a. Okay, your second boundary condition says that x prime of L equal to 0. Okay, so now based on the updated solution that you have here, you can see that x prime is now 0. Or you can simply look here, x prime. Okay, so if you want to use this boundary condition, so it means at the left hand side here it is 0 because x prime of L equal to 0. Okay, so you have 0 at the left, so equals at the right hand side b is already 0, so you have 0 equal to 0. So it means by using the boundary condition x prime of L equal to 0, you are basically get nothing. Okay, or we can simply say this condition, okay, this condition is not affected to the A. Okay, it's not affected A. Okay, meaning that you still cannot get your A from here. So your current solution is still this one. Okay, X is A. Okay, so what we can conclude, okay, for at this moment, the solution for the equation 1 is X equals A. Okay, some constant A that need to be determined later. Okay, so we have the solution for the x, we have the solution for the equation 1. So it is not 0. Okay, so meaning that we need to proceed with the equation 2. So equation 2 is t prime. Okay, equation 2, if you can look here, equation 2 is t prime minus lambda alpha square t. So now we are discussing lambda equal to 0. So the equation 2 becomes t prime equal to 0. Okay, again this is homogeneous with first order derivative only, so we have m only, m equal to 0. So we have single root, we need to treat this one as distinct case. Okay, so for distinct case we have t, the solution would be t of t equals we already have A, we already have B, so this is C. Okay, in terms of distinct solution, so normally we have C exponent M1 T. Okay, so basically in general it should be like this, exponent 0t. So since this is 1, so basically you can ignore that part. Okay, so you just have t equals c. Okay, so that is the solution to the equation 2. Okay, so if we put together t and x, because we know that by the equation star, okay, by equation star, uxt is given by x times t. Okay, so we have x times t here. So that is a times c, okay, which can be written as d. Okay, so uxt equals, so we can write as d, where d is a times c. Okay, so what it means here, we can conclude that this is the solution for case 1. That is when lambda equal to 0. So this one is slightly different compared to example 1 that you had before. Okay, if you can refer to example 1, case 1 is out of interest. Okay, but not for the insulated case. Okay, for the insulated case, case 1 is working. Case 1 is valid. Even though it is constant, it is valid. It is not 0. Okay, so we have the solution for case 1. We need to proceed with the case number 2 where lambda is positive. Okay, for case number 2, we are going to assume lambda equals p square. Okay, to guarantee that lambda is always positive. Okay, so we are going to let lambda equals p square. Okay, so again, we start from equation 1. So from 1, when lambda equals p square, then we are going to have x double prime minus p square x equal to 0. Again, this is homogeneous equation. We have m square minus p square, okay, equal to 0. So here our m1, okay, and m2. So we have m square equals p square, then m is the square root of p square, so we have positive p and also negative p. So we have two different roots, so the solution would be in the form of x of x equals a exponent of px plus b exponent negative px. Okay, so this is our initial solution to the equation 1. All right. Now we are going to find a and b. Find a and b by using boundary conditions. Boundary conditions in step 2. Okay. So the boundary condition that we have in step 2 in terms of derivative. Okay, so it means we need to differentiate the x prime first. Okay, so from the solution that we have, so we need to differentiate. Okay, only then we can apply the boundary conditions that we have. Okay, so differentiate x respect to x. So you differentiate the exponent. So you have p a exponent px minus pb exponent negative px. Okay, basically you can factor out p, then in the bracket you have a exponent px minus b exponent negative px. Okay, so this is x prime. Okay, only then we can apply our boundary condition. The first one is x prime 0 equal to 0. So we have at the left, we have 0. At the right, we need to put the small x equal to 0. So what happened to the exponent? So it becomes 1, okay, because you have exponent of 0x. So exponent of 0p, which is 1. Okay, so you have p, and then in the bracket, you have a minus b. Okay, now we need to think which one should be 0 in order to have valid equation here. Okay, so the same justification as you have in example 1, you need to say we can see that p cannot be 0. Okay, p cannot be 0 simply because lambda equals p square. Okay, this is always positive number. Okay, so if we let p equals to 0, then we disobey this one. So p cannot be 0 in order to maintain lambda equals p square. okay, which is not 0. Okay, it should be always greater than 0. So we say that P cannot be 0. So the one that need to be 0 is A minus B. Therefore, A minus B need to be 0 in order to have equation here equal to 0 at the left. Okay, so by that we have A equals B. Okay, so then we update our solution. So we update our solution. So now we have x of x equals. So you can update the A or you can update the B. Okay, so I'm going to let B equals A. So then I have A. Then I have exponent px plus exponent negative px, okay, because here b here is equals a, so I factor out the a, so in the bracket we have here, so that is your current solution. Now by the second boundary condition, we have x prime of L equal to 0, okay, so we have that. So from the current solution that we have, okay, so x prime, okay, this one here, okay, so based on this, or basically you can refer to this one, okay, so x prime is 0, so at the left you have 0, at the right, okay, we need to substitute x with L because this is x prime at the point x equals L, okay, so we have P, okay, A, exponent PL, okay, minus exponent negative PL. Alright. And then we know that, okay, the same justification as here, okay, so this P here cannot be 0 to maintain this one, okay, so we want to have lambda equals P square, which is always greater than 0, alright, so P here cannot be 0, then, okay, if P cannot be 0, then the bracket, the terms in the bracket, which is exponent PL minus exponent negative PL, also will not be equal to 0. Okay, because these terms here will only be 0 if P equal to 0. Okay, so since P is not 0, so automatically it means that this whole thing is here, okay, also not equal to 0. Okay, so the justification here is since P cannot be 0. Alright, so since P here is not 0, the bracket here is also not equal to 0, then the only thing that need to be 0 is A. Okay, to make sure that we have the term at the right here is equal to 0. Okay, so we can write therefore A need to be 0. Okay, so when A equal to 0, see what happened to our solution. Then we have from here, okay, when A equal to 0, x will be 0. Okay, so we have x of x equal to 0. Okay, our solution, current solution. Okay, by the equation star, if x equal to 0, then u xt will be 0 because u is x times t. Okay, okay, so this one again is not valid, not a valid solution. Okay, because again you need to think of your rod. Okay, so it is not true to say that at any point x at any time t the temperature is always 0. That's not valid. Okay, so it means that for lambda positive, okay, we don't have a solution. We ignore this case. We don't have a solution. Okay, but before this. Okay, for case 1, we have the solution. Okay, but for case 2, lambda is positive, we don't have the solution. All right. So now we have one more case, that is when lambda is negative. Okay, so case 3, the case 3, that is when lambda is negative number. So we are going to assume lambda equals negative p square, okay, to ensure that we always get the negative. Okay, again, we look at equation 1. Okay, when lambda equals negative p square, then we have x double prime plus p square x equal to 0. Then by the homogeneous solution, we have the characteristic equation m square plus p square equal to 0. Then m square is negative p square, so m basically in terms of complex. So m equal plus minus pi. Okay, so we have complex form. Then therefore our solution should be in the form of exponent alpha. So in this case, alpha is 0. So we have 1. And then we have a cos px plus b sine px. All right. So we have that. That is our current solution. Okay, now find a and b, okay, by using the boundary conditions that we have in step 2. All right. So first of all, we need to differentiate x because the boundary condition in terms of derivative. Okay, so first of all, we need to get this one, x prime. Okay, you basically differentiate x with respect to small x. Okay, so you differentiate cos, you have negative sine, so you have p a negative pa sine px plus pb cos px. Okay, that is your derivative. Okay, and then you can apply the boundary condition. The first one is x prime of 0 equal to 0. Then we have on the left it is 0, and at the right we need to substitute x equal to 0. Then we have 0 here plus pb cos 0 is 1. So we have pb. Again, p cannot be 0 because of this one here. We don't want to have p lambda equal to 0. Okay, so if p equal to 0, then here we have lambda equal to 0, which is case number 1. Okay, we don't want that. We want lambda to be less than 0. So it means p cannot be 0. Then the only thing that need to be 0 is b. Okay, b equal to 0. Then with that, we update our solution. Okay, then our solution is, okay, so remember you need to update this one, not the derivative. Okay, because x is the solution. Okay, so we update our solution. So now we have x of x equals a cos px. Okay, this is our updated solution. All right, and then we try to get the a now. Okay, so by the second condition, it says that x prime of L equal to 0. Okay, so on the left hand side again here, okay, we have 0. Okay, at the right hand side now, we need to substitute x equals L. Okay, x equals L. But ignore this part because this is already 0 because of the b equal to 0. Okay, so we only have negative PA sine P L. Okay, x equals L. Okay, so again, P cannot be 0. Okay, P cannot be 0. And then A cannot be 0 as well. Okay, because if a is 0, then we don't have the solution. Okay, this is our current solution. If a equal to 0, then x going to be 0, then everything will be 0. Okay, so a cannot be 0, and then what's left is just this sine PL here. Okay, so therefore sine PL need to be 0. Okay, so think of what is the PL so that your sine PL is 0. Right? So sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, so on and so forth. So basically we have PL equals n pi. Okay, because if PL equals n pi, then we can see here that we have sine n pi, which is always 0. So PL is equal to n pi, so that P equals n pi over L, where in this case n equals 1, 2, 3, so on and so forth. Okay, n is a positive integer. So with that P, now our current solution will be, so we go back to the x. So x equals a cos, okay, P now is n pi, and then we need to multiply with the x, so n pi x over L. All right. So n, okay, start from 1 up to positive infinity. Then, okay, for n equals 1, we have the solution x1 equals a, okay, e1 cos pi x over L. When n equals 2, we have another x, okay, x2 equals a2 cos, okay, 2 pi x over L. So we have lots of solution, so therefore we can denote the solution to be in the form of subscript. Xn x equals an, okay, an cos n pi x over L, where our n is a positive integer. Okay, so that is our current solution. So we have that one, our current solution. Okay, so since we have the solution for the x, meaning that we need to proceed with equation 2. Okay, equation for the t. When lambda equals to negative p square, then we have t prime equals t prime plus p square lambda square t equal to 0. Again, homogeneous equation, okay, first order only. So we have m plus p square lambda square equal to 0. So basically m equals negative p square lambda alpha square. Therefore, the solution would be t of t equals so we can write e now, okay, constant e exponent negative p square alpha square t. But since p is n pi over L, therefore we have t and t equals e n exponent negative n square pi square alpha square over L square times t. Okay, because P is n pi over L. Okay, so that is the solution for the t. Therefore, by this equation star, the solution would be then uxt equals a an. This is for the x, an cos n pi x over L. This is x, okay, and then times t. Okay, so t is en exponent negative n square pi square alpha square L square t, which can be simplified as an. So I'm going to denote the capital A times capital E as an. So we have an cos n pi x over L times exponent negative n square pi square alpha square over L square times t. Okay, so this is the solution for the case. Okay, solution for case 3. All right, so meaning that for the insulated case, we have the solution for case 1. Okay, we discard the solution for case 2, but we have the solution for case 3. All right, so proceed to next step. Okay, now step 4 is to sum the solution that we have from all cases. Okay, so from case 1 we have the solution, and from case 2 we also have the solution. Okay, so the solution uxt equals, okay, from case 1, that is D. Okay, you can refer to the solution in case 1. In case 2 we don't have the solution, that is 0. And from case 3, okay, that is what we have up here. Okay, so an cos n pi x over L exponent negative n square pi square alpha square over L square times t. Okay, that is n from 1 to 3 up to positive infinity. Okay, so we have lots of solution, okay, because n is a lot. Okay, so by the superposition principle, then we can write uxt as d plus the summation n from 1 up to positive infinity. Okay, then we have an cos n pi x over L exponent negative. Okay, so you can write like this, n pi alpha over L square times t. Okay, now I want to explain to you why we can rewrite this thing here to be in the form of summation. Okay, some student might question why we have the summation here. Why not the summation start from the beginning here? Okay, why here? Okay, so I'll explain on that one. It is called the superposition principle. Okay, so in brief, I can write if x1 is a solution to a certain problem and x2 is also a solution, then x1 plus x2 is also a solution. Okay, so I'm going to take a simpler case of the solution that we have just now. So we have uxt equals, I'm going to take just d plus an only. Okay, I'll just ignore the cos exponent and so on. So n equals 1, 2, 3, so on and so forth. All right. So when n equals 1, then we have u, okay, at the left, uxt equals d plus a1. Okay. And then when n equals 2, we have another solution uxt equals d plus a2. When n equals 3, we have another solution uxt equals d plus a3. That is, okay, if we consider n from 1 up to 3. By the superposition principle, it says that if x1 is a solution, okay, x2 is also a solution, then the combination in terms of summation is also a solution. So it means that from here, if d plus a1 is a solution, d plus a2 is also a solution, d plus a3 is also a solution, then we can have, by the superposition principle, the combination in terms of summation, d plus a1, okay, plus d plus a2 plus d plus a3 is also a solution to the u. So we can write 3d plus a1 plus a2 plus a3. Okay, so 3d here is just a constant, so that's why I just can write as d. Okay, or we can have another constant okay, f for example, but this is okay to remain as d because okay, it is still a constant. Okay, 3 times d is also a constant. Okay, so we can see here that this is can be written in the form of summation, and from 1 up to 3, so we have an. Okay, so in our case, okay, just now we have n from 1 up to positive infinity. So basically we have lot more of a up to a when n is infinity. So that's why we can simplify the terms, the summation here to be in the form of summation notation here, and from 1 up to positive infinity. Okay, so this is what we call the superposition principle. Okay, I hope you're clear on that. Okay, because sometimes students just memorize the solution without knowing why they write in terms of summation. Okay, so back to our solution. Okay, so this is our current solution, UXD. So we can see we have D and AN that need to be determined. Okay, so we need to find D and AN. All right, so now from the initial condition given, okay, from the initial condition that is given to us in the problem, so it says that ux0 equals x. Okay, so this is the initial condition. So now we can directly apply to this one. Okay, because this is given in terms of u, not in terms of derivative. Okay, so when t equal to 0, the u is x. So at the left, we can have okay, x equals d, okay, plus the summation. Okay, and we substitute here, okay, at the this terms here, t to be 0. So when t equal to 0, the exponent here becomes exponent of 0, which is 1. Okay, so what we have is just cos, okay, an cos n pi x over L, okay, when t equal to 0. All right, so now how do we get the D and AN here? Okay, so if we look closely, this is what we have in chapter 4, the Fourier series. Okay, if you can still remember, so we need to map this one to the Fourier series because we have, for the case of even function, then fx is given in the form of fx equals a naught over 2 plus the summation and from 1 up to positive infinity an cos n pi x over L. This is what we have, okay, in Fourier series. Okay, so that is why I denote at the first place I denote our constant here an times en to be the small a, okay, an. Okay, and that is the notation that we use in the Fourier series. Okay, so by mapping what we have, okay, so we have here, okay, and D is mapped to the A naught over 2 and AN is mapped to the AN. This is also the same thing. Okay, cos n pi over L. So if L is given to you as 2, for example, okay, then the capital L is straight away 2. All right. So by mapping the expression that we have to the expression in the Fourier series, we know that fx, okay, is actually x in our case. Okay, a naught over 2 is basically d in our case. So an in the Fourier series is also an in our case. Okay, L in the Fourier series is also n in L in our case. Okay, so it means that if we can get the a naught, if we know the formula for the a naught, so of course we can get the d because d is basically a naught over 2. Okay, so by the Fourier series, a naught is What is the formula for the A naught? A naught equals 2 over L, integral from 0 to L. Okay, or before this you have the small l. Okay, doesn't matter. So 0 to L fx dx. Okay, so in our case we have L is also L, so 2 over L, 0 to L, our fx is x dx. Okay, so straight away we have 2 over L x squared over 2. We evaluate from 0 to L. Okay, so cut the story short, at the end we are supposed to get L. Okay, substitute x equals L minus whether x equal to 0. Okay, so simplify everything. We have our A naught is L. Okay, so therefore, since D is A naught over 2, then we have L over 2. Okay, so that is our D. Okay, we are going to put that later, okay, in our final solution. Okay, so now what's left is the AN. Okay, so by the Fourier series, AN is 2 over L, integral from 0 to L, fx times cos n pi x over L dx. Okay, so in our case, we have 2 over L as well. So the limit is L, 0 to L. Then our fx is x times cos n pi x over L dx. Okay, so again, this is by parts tabular. Okay. Okay, make sure you have this by the tabular or by parts. So I'm just going to write the solution here. Lx over n pi sine n pi x over L. Okay, plus L square over n square pi square cos n pi x over L. Okay, evaluate from 0 to L. Okay, so when when x equals L, so we have 2 over L. Okay, L square over n pi. Okay, sine n pi. Okay, x equals L. Then we have L over L, which is 1. So we only have that. Okay, plus L square over n square pi square cos n pi. Okay, when x equal L. Okay, so that is when x equal L. Okay, minus with the x equal to 0. You can see when x equals to 0, this term here is 0. Okay, 0 plus with the L square over n square pi square, and cos 0 is 1, so we just have that. Okay, and what we can simplify is this one. Sine n pi is always 0 and cos n pi is negative 1 power of n. Okay, that's what you have earlier in the Fourier series. Okay, so we can simplify an to be 2 over L. So in the bracket we have L square over n square pi square negative 1 power of n minus minus 1. So basically I can factor out that. Okay, and factor out the L square over n square pi square. So okay, furthermore we can simplify this L and this L. Okay, so we have 2L. Okay, so therefore our final answer, okay, so put things together, so therefore our solution, okay, to be, okay, so go back to the ux t here. So this is our solution. So put back what is your d, what is your an. So just now d is L over 2, and then we have the summation n equals 1 up to positive infinity an. So an is 2L over n square pi square negative 1 power of n minus 1. So the whole thing here multiplied with the 2L. So we have cos n pi x over L. Okay, and then exponent negative n square pi square alpha square over L square times t. So that is our solution for the insulated case. All right, so 4 to 5 steps altogether. So hopefully, okay, you can understand.